Like in the TLC, I was about to be like, move, but then I was like, they're middle schoolers,
17th
that's
lecture.
me. No need to be
Okay.
hostile. Huh?
I don't have any classes to go see this semester.
Oh, that's nice.
You just need to hold this before.
Yeah, no. This is about to get not my problem. Keep walking. They get body slammed by someone. I don't want to hear that. So.
If it's Sunday.
Yeah, they're like, dude, come here, like.
Hello.
They're like, oh, a person who's the same size as me yelling at me.
So maybe
Dude, in pajamas in the same mood.
He was in a wait for a while.
Okay.
So
Because I was sick, because
Okay, I also have the attendance slide at the end, so don't worry about if you're like walking in now. So I usually started earlier because we're just not doing anything while waiting to become 9:30. Okay. So anybody who didn't do the attendance, just do it right now, or for whatever reason, if the link doesn't work, just let me know. So I'm going to post the homework 7 during the weekend, and then the deadline would be on Wednesdays like usual. So remember, if you have like an excuse reason that you cannot do the homework, just communicate that with me in advance. Not like 1 hour before. So, and then prioritize your work. So don't let the homework be the last thing you do on Wednesday, because things can happen, right? Okay. So, first, I want to talk about tutoring. And as I told you guys from the start of the semester, I'm going to devote 5 points for each tutoring session that you attend. So we have workshops on Mondays now, so they used to be Mondays, and then we switched to Thursdays, and now they are like Mondays again. And even if you cannot make it to Sean's workshops, you are welcome to just walk in tutoring or like make an appointment. And we have like Dale Homer in our session today. So he is tutoring program coordinator at the UI, and he's your guy. So reach out to him and schedule tutoring. And as we progress with the course, you'll see that the course is going to get more difficult. I'm going to teach faster because I should cover more chapters. And I cannot just like tell my chair that I covered like 3 chapters. That is not how it's supposed to be. So I'm going to teach faster, and you need to study harder and also take advantage of tutoring. So I'm going to let Dale talk about tutoring.
Yeah, how's everybody doing? Yeah, so I just want to say thank you for coming into class today. Despite how freezing cold it is outside and how miserable cold it has been all week. But one thing I want to say is I want to thank the students who've been coming for tutoring so far, because Chemistry 275, in terms of our chemistry sections, has been one of our highest attended sections. So starting next week, yes, Sean will still be your primary tutor for this class. His hours on Monday will actually be 4 to 8. So you're able to come on Monday now between 4 and 8 to meet with Sean. And every week you will get an email in terms of what's available for this course for tutoring. But also starting next week, we're actually going to have a total of 4 tutors throughout the week that is able now to cover this subject. So Monday through Thursday, as it shows on the slide, you will be able to come in for Vandal's tutoring and get help in this class. And as your instructor mentioned, you get extra credit for coming to each session. And when your instructor requests it, I will email her in terms of those students who've been coming, so you can apply those extra credit points to your final score, whether it's for the midterm or for your final. But Monday through Thursday from 3 to 8, but you also will see emails from me throughout the semester. Like each week, I'll say like this is the times where we'll have someone dedicated just for Chemistry 275. So example, Tuesday we'll have someone from 4 to 8. And Wednesday we'll have someone from 6 to 8. But that, again, it will have someone be available every single day in the library to assist you in this class. At this point, I just want to ask, does anyone have any questions about the tutoring service that we offer? So again, I just want to say one more time, you're getting extra credit for coming to tutoring, so please take advantage of that, because it is a really good benefit that you will have, and it will possibly benefit your final grade. So I'll turn it back over to your instructor.
Okay. And sometimes the students have this perception that if they go to tutoring, it means that they're not doing well in the class, or other people see them, they have tutoring. This is not the case for most classes, including this one. So most of your friends that are doing really well in the course, they go to tutoring. So what ends up, when I'm adding the grades, instead of like having 100 out of 100, they have like 150. Sometimes last semester I had someone that they were like, 160 in the course. So what happens is that usually students who are doing well, they go to tutoring because they want to take advantage of like tutoring sessions. So I encourage everyone, if you're not doing well, if you're doing well, everyone, is welcome to go to tutoring, and I encourage it. And what I started to do, like from like last 2 tutoring sessions, I print out extra questions and extra materials that I'm going to design, like homeworks, quizzes, exams, and so on and so forth. I give them to the tutor, and I also give them to the students who go to that tutoring session. So if you go to tutoring, you have answer to some questions, and your tutor explained that to you. So I don't really see a reason why you shouldn't go, unless your schedule doesn't let you to go. That we have like so many hours for tutoring, as you can see. So I think the chances are high that one tutoring session will work out for you. But if none of them works out for you, just reach out to me myself, and I schedule tutoring with you, because I want you all to have like extra credits, okay, and learn the material as well. Any question about tutoring? Okay, thank you so much. Okay, so let me go to the next slide I have. So last session, we talked about halogenation. So the other thing that I really want to emphasize, from now on specifically, you're going to need to read the book. And I cannot emphasize it enough, And this is kind of like the college structure. Just sitting in the class and just reading the slides, it will not do. You should study the book, okay? And I expect you, I try to have like most of the materials that I asked you in the slides, but you need to refer to the book to understand all the materials well. So kind of here, I have like the summary of what I talked about before, and also, adding some points, kind of like emphasizing that, we had like chlorination, bromination, or halogenation in general. And they were types of substitution reactions, right? That we substitute a hydrogen atom with a halogen. And also something that I briefly mentioned last session, you may see something like this in your book. So what it means is that CH3Cl is reacting with Cl2. So we write one of the reagents on the arrow. And here, the product, if you have like another Cl2 here, one of these hydrogens substitutes this chlorine, or like we switch place, right? It's substitution reaction. And here is plus HCl. And most of the times when we become experts in these subjects and we write these reactions a lot, we think that the inorganic compound is not necessary to write. We already know we have HCl. So I just wanted to emphasize this fact, okay? And also sometimes you see reactions, especially when you have like several reactants and products, and you notice that the reaction is not balanced. So sometimes we just want to focus and emphasize of the reactants and products. So that's why sometimes we just like don't write the, don't balance the equation. Any questions? Good. Okay. And when we wrote, and these are like the summary, and kind of a review of what I wrote before in the previous slides. And you remember that if we have excess halogen, the reaction can proceed. Now another hydrogen substitutes with chlorine atom, and then it can occur again, right? And we can have polyhalogenated products. it means that they are like they have several. Poly means like multiple, right? They have like multiple halogens. And if we have, if we control the reaction conditions, and we talk about these reaction conditions more as we progress with the course, we can adjust the ratio of our halogen and the ratio of halogen to methane, or like depending on what alkane we have, like that halogen to that alkane. So if we want like to favor the formation of one specific product by controlling reaction conditions, we can achieve that, okay? And if we have like larger alkanes and we do halogenation reaction, so here we had like, excess halogen, and in each step, one hydrogen was being substituted with chlorine. But sometimes when we have like longer chain alkanes, what happens is that at the same time, we can have multiple products, right? And again, we had like some examples of these I wrote in the previous slides, so I'm not going to repeat them. So go back to the slides and also read the book, so these things make sense. But since I'm going to ask these in your homework, I just also included them here, so make sure that you know all of these materials. And for this reason that I just mentioned, because if we have like a long chain alkane and we can have like multiple products that they have halogens, sometimes it's like difficult to get the desired product. For that matter, these halogenation reactions tend not to be a useful way to synthesize a specific alkyl halides. Okay, so if you want to have a specific product, usually halogenation is not the best option because we can have multiple products, right? And most of them necessarily are not the ones that we want. Does that make sense? Any questions so far? Okay. And just this point that I just mentioned here, if we have like unsubstituted cycloalkane, meaning that we just have like a cycloalkane by itself, and I might example might not. Let me go to your book and then show an example here. And what I'm showing is like page 59 in my book. For people who are watching this at home, let me go here. You see, if I have unsubstituted cycloalkane, for instance, cyclopentane, right? And if I want to substitute one of the hydrogens with Br, for instance, here, I have like how many, if I consider this point here that I have my pen at, how many hydrogens are here attached to the carbon? Two, right? And maybe it's like, so, okay, I'm going to write that quickly afterwards. So if I substitute one of them with bromine, it is just like one possible configuration, right? So, or at least it would be like just one. If I just like put it also here, 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 all of them, they would be the same. So they can be like different in space, right? But in the paper, or like in the sense of being like structurally, they are like the same, right? Because all of these are like equivalent. So for that matter, if I do halogenation for like unsubstituted cycloalkanes, meaning that they don't have any branches, right? Remember, substituted branches here. So all of these would be equivalent, so I just get one product. So here it would be like cyclopentyl bromide or like bromo cyclopentane. Remember naming these? So we studied the IUPAC naming. So we call this bromo, and then we don't write one bromo. Is that clear? Yeah. Okay. So let me switch to what I was writing here. Okay, and also I add this example here, and I also wrote that in the previous slides or like sessions. So if I have like cyclopentane, so what I was pointing was here. If I substitute one of these with one BR, then I should have light here. Like we used to draw houses like this when we were a kid. Like. So it's like BRH plus HBr. So if I have unsubstituted cycloalkanes, where all of the hydrogens are equivalent, a single pure organic product can be obtained. And these things I asked you true or false in the homework that you're going to see in the weekend. That is the following statement, true or false. If we have substituted cycloalkanes, so if we have like, if I have the same structure, but I have like a methyl here, right? And then in that case, if I substitute one of these hydrogens with Br, that would be different compared to substitute one of hydrogens here with Br. Does that make sense? Because the bond ordering and what atoms are bonded to would be different in this case. But if I don't have any branches, all of these would be the same. Even if I just substitute the other hydrogen here with Br, the structure on paper, the bond ordering and everything would be the same. Any questions? Good. Root and okay, and again, I went to this website, Khan Academy, and I realized that the guy that was explaining that, did a really good job. So I also included free radical reactions in this video. So in case, I'm not explaining well or you have like difficulties, sometimes, when you just like watch a video, it helps us to understand much better. So I also included this, and I encourage you to watch it. It's like 15 minutes. And I think it's really useful. And here, again, we talked about this in the last class, but I thought it would be useful to also like go through them really quickly. Remember, if we have like, chlorine molecule, and then we have like an alkane, and then if we just like put them, next to each other in room temperature, nothing happens, right? So we should have like light or, heat. We should give them some energy for this reaction to occur. So if that happens, the first thing that happens is that we have like initiation reaction. And this is kind of like the reaction mechanism. Remember, we talked about reaction mechanism in the last session. So we say exactly what happens in the sense of bonding. So we would be having like two chlorine atoms. And these are, they have like odd number of, unshared electrons. So for that matter, these can be considered radicals. And the second step is propagation, that it consists of two steps itself. So when you have like these chlorine atoms, they are highly reactive, and they want to react with the alkane you have, basically this RH. And remember that when we had an alkane, and then if we remove a hydrogen, we get an alkyl, right? And alkyls are also radicals. So we denoted them with R. So if you go reverse, if we have R radical and we add a hydrogen, we have a alkane. You have an alkane, right? So your alkane reacts with like one of these Cls, and then you have like this radical plus HCl. And this slide that I included here in your homework, I'm gonna ask which of the following is not part of a propagation step, or which one of the following is initiation. So you should know which of them is which. And then here you have like just like the R radical. You may wonder why this R wouldn't react with another Cl, right? So when you have like the first step initiation, now you have like free radicals, imagine all the compound that you have, all the molecules, now you have like two of these radicals. So one of them reacts with your alkane, but now these are, the chances of that reacting with that exact chlorine atom is low. chances are that this radical now encounters another Cl2 molecule. Does that make sense? Yes.
I just want to confirm that these are bonds, not subtraction. Right?
Yes.
Okay.
Yes. Exactly. Yeah. You can also show them with dots, like 2 dots in between them, but yeah, we use a dash, you know, kind of like, yeah.
Just with the plus sign there. It was
Yeah.
Is that a subtraction or?
Yeah, yeah. Great question. Thank you for clarifying. Okay. Any other questions? So now we have like, you know, RCl. So basically you substituted one of the hydrogens with chlorine and with like one of these chlorine atoms. And again, we show the transfer of electrons, 1 electron with these arrows. Okay? And in the last step, again, all the radicals come together and form compounds. So it can be like Cl plus Cl, it can be like R plus R, it can be R plus Cl, kind of like all possible combinations. And then you have your final products here. Is that clear? And you know, in the exam or your homework, I substitute these R's with, you know, radicals, and I write alkanes here. So you should, if you know the structure, you can just like, you know, solve the questions. And the other thing, you know, I advise you to do for your homeworks and quizzes, those are open book, open notes. I advise you to just like take the, you know, answer one question. Even if you're sure you answered it right, just check your notes to confirm, because why shouldn't you do, right? And, you know, I advise you to first answer it yourself and then check your answer so you learn. This is kind of like learning process, the homeworks and quizzes. Included this from your book, that remember that when we had like this, you know, fish hook or half-headed arrow, we have like movement of odd number of electrons, right? Movement of only 1 electron. Whereas we use a complete double-headed arrow to describe the movement of an electron pair. So that's why, you know, just like, again, these things that we agree to show in this way, right? So if you have like just like this type of arrow, we have the movement of 1 electron. But if you have like complete arrow, it's like 1 pair of electrons are being moved. Okay? And here again, you know, free radical chain reaction includes a chain initiating step, chain propagating steps, and chain terminating steps. So basically initiation, propagation, and termination. Okay, talked about this. And the other thing that is important to know is that the Cl-Cl bond is weaker than CH bond or CC bond. In other words, Cl-Cl has the lowest bond energy. So for that matter, if it has the lowest bond energy, do you think it's easier for us to break it or harder?
Easier.
It's easier, right? So when you give like heat or energy or light to these compounds, if you have like halogens or like Cl2 specifically here in this example, and then an alkane or like methane in this specific example, you know, Cl2 bonds will break first because the bond energy is much lower. Okay? And this is basically the point that the book discussed here. I just wanted to touch base on that. Any questions so far? Okay. Now I'm going to solve some examples so you will be more comfortable answering homework questions. And the other thing that I advise you to do is that on the back of your books you have some problems and you can certainly working on them. And here I write like problems 247 to 254 specifically are like reactions of alkanes. So, reactions of alkenes. And I encourage you to go through them, solve them, and if you have any issues, reach out to me, reach out to your tutor. And I already gave these questions to your tutor, and he solved them for some of the students that went to tutoring last night. And from now on, tutoring would be like on Mondays. Remember, as Dale mentioned, like 4 to 8. And yeah, so I encourage you to solve more problems and ask me if you have any questions. So when you do the homeworks, you won't be having much difficulty. Okay, so here I asked you how many monobromination products, or rather your book asked, can be obtained from each of the following polycyclic alkanes. So we have like 2 of these rings in a sense. So we have like a polycyclic alkane, right? And when we say monobromination, it means that we want to substitute 1 hydrogen with 1 bromine. Okay, and I'm asking you how many different products can be obtained. And in these types of questions, I just asked you about structural isomers, meaning that I don't ask you about like stereoisomers, because sometimes you have like on paper 1 compound, and in a space, if you rotate it, as we talked about like conformational isomers, you get the same structure. So when I give you these questions, I expect you to know how many structural isomers, meaning that the atoms are arranged differently, in the bonds that they are like forming. Does that make sense? So here, how many do you think, or can anyone guide me if I want to substitute, like, if I write this, like, how many hydrogens do I have here? 4, right? And then here, 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 here. Maybe I can just like zoom this, okay? Here, and here, and here 2, and 2. Is it obvious for everyone how we write these? Good. So now, if I want to substitute a hydrogen with 1 Br, right? How many possible configurations or how many possibilities do you think would exist? So here's the point, that the thing that you're saying is right, in some ways, but we're just talking about structural isomers. So if you, for instance, if I, substitute this hydrogen here, right? So I have like 2 hydrogens. I substitute 1 of them, right, with Br. So I have like 1 of these hydrogen I substituted with Br, right? If we consider that one, that is, forming bond with 1 CH2 and 1 CH here, right? And then if I consider this one, right? Imagine 1 of these hydrogens I substitute with Br, right? That one is again bonded with 1 CH here, 1 CH2. So these 2 are actually the same, right? And this is how you distinguish structural isomers. You look at the bonds and the branches, or like atoms, that a specific atom that you're considering, in this case Br, bonds to, right? So if I add it here, right? What happens if I add the Br here? Here your CH, so here it's just like 1, 2, 3 bonds, so it would be CH only, right? CH1. Because the valence of carbon is 1, you already have 1, 2, 3 bonds, and then you need 1 hydrogen, right? And then you consider this Br, you say that this carbon here right now, or like this Br is between 1 CH2, 1 CH, and another CH here. And then if I add the Br here as well, just like cluttering here, if I add it here too, again, that forms a bond, here we have CH, and then it would be like the same as here, but just like different 3D arrangement. Does that make sense what I'm saying? But if you write it down, it would be like, you know, you have like this Br here, having a bond with like CH, 2CH, 1CH2. Here again, 2CH, 1CH2. So for that matter, we consider that one possibility. Does that make sense what I'm saying? Kind of. So for that matter, you know, one possibility would be here, that I substitute Br here. The other would be here, and the other would be here. So there would be like 3 monobrominated structural isomers. And if you know, kind of like go through this problem in more detail and then write the other possibilities, you realize that, for instance, if you put like Br instead of here, like here, that would be again the same as this one. So they are like the same if we consider their structures. Any questions? Or like the same, like as like this one. No, if I put it here, it's basically the same. But here, remember, here we have like a, you know, before I put the here, you know, if I don't put the, I have like, before putting the bromine, I have like 1, 2, 3 bonds. It would be CH, this would be CH2, this would be CH2, and then this would be like CH2, CH2. So basically one possibility would be like putting Br here between 2 CH2. One would be putting here, you know, between 2 CH2, but here itself it has like 1 less hydrogen. And the other possibility would be just putting it, so one would be here, one would be here, and one would be here. Any questions about this? Is that clear how we do that? Yes.
So if you were to like put the bromine for the first one on the bottom instead of the top, would it still be considered the same?
So
Like the same bond, just on the other side.
okay, so which of these possibilities you're talking about?
One.
So if I just put this here, you mean?
Yes.
Yes, so this would be exactly the same.
Okay.
Because if you just like rotate it,
Right.
so these are like the same. And the way that you know, realize that is that here you have like CH2, here you have CH2, here you have CH, and again here you have CH, CH2, CH2. So those are basically the same.
And you
structural.
can write it either way and
Yes.
it would be acceptable?
Exactly.
Okay,
Yes.
so then for like number 2, there's 4 different options, right? For that same bond?
Yes.
Okay,
Yeah.
perfect. Cool.
Yeah. Great question. Any other questions? Okay, now let's do another example. So what about this one? Yeah. You're welcome also to just like work on it for like 1 or 2 minutes. Or like discuss it with your friends if you like. Yeah, I had a hard time to just like draw this, and it was just like being distorted. And this is like the best I could.
Yeah, it looks evil.
So what I advise you to do is that to put like C and hydrogens there to know how many CHs you have, how many like CH2, how many CH3, and the ones, again, you know, remember that if you have like, you know, CH3, CH2, CH, and this is how you can distinguish which ones are equivalent and which ones are not. Okay, you consider your bromine and then what bonds it forms and how many bonds. So you can just delete this. Okay. So everyone could put like the carbons and hydrogens there. Okay. So you see, what color do I want? Okay. So one possibility would be to substitute this hydrogen with Br, right? And when I do that, I will have like this structure here, right? Substituting this one with Br. The other one would be to substitute this hydrogen with Br. So I'd be having like this structure. And the other one would be like substituting one of these hydrogens. And then each of them you consider are like the same with Br. So you will be having like 3 structural isomers. Any questions? Does anyone can find another isomer that I'm like missing? That you can think of that would be like different from one of these guys.
On the corners for CH2s.
This one? You mean?
I can't see it clear. Yeah, that one there. Yeah.
Okay. Yeah, sometimes I just have my pen. I feel like I have like dot cam. Okay, so let's see. Let's see if that one is different. So if I consider this one, and then I substitute this one with the Br. So I'll be having like CH here, right? Because I have like 1 bromine now. And then that forms a bond with like CH2, and then 1 with CH, and then I have CH attached to it. So basically I have like CH, Br, and then here H, CH2. If I just like consider this portion, right? So what about this one that I wrote here? Right? So basically this one, if I substitute, so here I have like CH, 1, 2, 3, so CH, and then here I have like CH, and then here I have like CH2, right? So basically this one and this one are like the same. If I just flip them, you know, the other, so if I rotate them, so these are the same basically. They are like stereoisomers, but they are like the same structural isomers. And this is how you can like, you know, test, you know, as your friend said, you can just like write another structure and then just check that, do I have like Br form a bond with CH, and then those, you know. So if the bonds end up being the same, you have the same structural isomers. Okay, any question about that, this subject? Okay. So another question is that using structural formulas, write equations for the following halogenation reactions. The monochlorination of propane. And because I'm just running out of time, I did this, like write this, so you have like some sample again for the homework. So you know how to write, where was it? Write equations for the, okay, propane. You know that, right? What is the formula for propane? Right, remember, and now we're going to talk about alkanes and alkynes, so remember not to confuse them. So CnH2n plus 2 is alkanes. And when you want to write, you know, the structural formulas, you have like 3, you know, carbons, and then you have only single bonds, and you kind of like put hydrogens around them. So if that reacts with Cl2, what would be the result? Yes. So one possibility is that you substitute one of these hydrogens with Cl. So you write CH3, CH2, CH2, Cl, right? The other possibility would be you substitute this hydrogen here with Cl. So it would be CH3, CH, Cl, CH3, right? And again, if you substitute the first one, it would be like the last one because they have like symmetry. So they would be the same structural isomers. That's why we just substitute one of them. But you're welcome to write like CH2Cl, CH2Cl3 for the first one. So can anyone tell me what was, I mean, I have the answer, but does that make sense for everyone that why we call this 1-chloropropane? Right. And then why we call this 2-chloropropane? Remember naming, alkanes when we had like halogens? Okay. And finally we have HCl, right? Because we had like Cl, and then we broke this bond in a sense, and now we have like Cl atoms, right? And then one of these, we substitute this with hydrogen, so we have like HCl. Any questions? Good.
Both of them have HCl? Like, I don't know, or is that what you're saying? Both of them produce HCl?
So if you consider like the, reaction mechanism, so they produce HCl, but in the overall reaction, we just write HCl one time.
Okay.
So we have like 1-chloropropane, 2-chloropropane plus HCl. So in your book, you have like all of them next to each other. I didn't have space. I mean, I could have like do this, I guess, but I just wanted to be like zoomed in. But yeah. Any other questions? And finally, here is another example. And when you have like cycloalkanes, the possibilities can be more and the question can be more tricky. That's why I asked you to read the book and then solve some examples so you don't make mistakes in the homework, quizzes, and exams. So if you have monobromination of methyl cycloalkane, again, remember, if you have like just one methyl, we don't call this one methyl, right? It's just methyl cyclohexane. And when you want to write the bromination, there are like different possibilities. And again, you should write, I think I'm more comfortable with writing all the C and H's. So I know like CH, CH2 and all that. And for each of these, one possibility would be to substitute this hydrogen here, right, with Br. The other would be to substitute, maybe I can use highlighter, I guess. Okay, one possibility would be to substitute one of these hydrogens. The other would be to substitute this one, right? So the first one corresponds to this one, right? This one corresponds to this. And the other one would be to one of these hydrogens here. I substitute with Br. The other one of here. And can you guys all see that why this one is different from this one? Can anyone tell me why these are different?
One's connected to a CH and a CH2, the other one's connected to two CH2s.
Exactly. So you see, as your friend said, here, try to use my red. Okay, here in this one, you have like two CH, one CH2, one CH. Around it, here you have two CH2. So that's why these are different, right? And then here, and then the other possibility can be like, so one would be this, one would be this, the other, here, the other here, and then the other here. And depending on where you put that, we have like different names. And then this one, we didn't specifically talk about it in the class, but we call that one bromomethyl cyclohexane, but the other ones you should be able to name because we talked about this, like when we have like bromo, we have like halogens and methyl ethyl alkyl groups in like a ring, right? Cycloalkanes. So the other ones you should be able to name them. Any questions? Yes.
So 1 bromo 4 and 1 bromo 3. Why would those not be the same?
Okay, let me see. Okay, so here, so what is this one? This is like CH2, right? And then this is CH2, And what is this one? And then this one is CH2. And then this one is CH. Huh, they might be actually the same. But, okay, I think the other thing, that, so in the sense of just bonding here, they are the same, but their locations towards the methyl group is also different. So here you have like CH3, far closer to Br, but here CH3 is like further away. So technically, you cannot rotate them, if you have like the molecules in 3D, you cannot get the other one to get that. So we don't write them, or like we don't consider them being structural isomers if we can get the same exact structure by rotating in space. But in that case, because we have like CH3, that's more tricky. Great question. Any other questions? Also, let me go. Finally, does every one of you know how to write combustion reactions? So we talked about combustion reactions and oxidation reduction reactions, but I didn't give you guys a specific example of how to write combustion reactions. So remember, we have like complete oxidation or like complete combustion, and then we have like partial oxidation or partial combustion, right? So if you have enough oxygen and you have complete combustion, you should be able to write the combustion reaction. And how you write it is that, for alkanes, since you have carbon and hydrogen, if they completely react with oxygen, you will be having carbon dioxide and water, right? And then you should be able to write the structural formulas for compounds too, specifically alkanes. And next, you balance your equation. And can anyone tell me how to balance a chemical reaction? Any ideas?
Make sure they're equal on the same side.
Exactly. So how would you make sure that the number of atoms in each side is equal to the other side?
I only remember to do the single element last.
Okay, yes. So there are like several rules, but what I always tell to my students, and most of the times for the things that you see during our class that will do, is that the molecule or element that is by itself, so only has one element in it. It can be diatomic molecule, or it can be like one single element, like Fe, for instance, or like have a ion. So always do them last. Okay, so you consider oxygen, right? So hold on to that and balance the rest of elements. So let's start with like carbon. You have like 4 carbons on the left. You should have 4 to the right. So carbon is now balanced. And then for hydrogen, you have like 10 here, so you should have 10 here. So 10 divided by 2 would be 5, so you put a 5 here. And now counting oxygen on the right, so it would be 4 multiplied by 2 plus 5 multiplied by 1, right? Which would be 13. So in order to have like 13 on the left, you should divide 13 by 2, which would be 13 over 2. And then we multiply everything by 2 because we don't want to have ratios or like decimal points in a balanced chemical reaction, right? So it would be like this. So I also included an example so I can ask you in the homework. But if I even give you other alkanes, it would be like alkane plus oxygen gives like CO2 plus H2O. And let me, before going to attendance, I also have like some slides here. So again, remember that what is the general formula for alkenes? Exactly, CN, H2N. And then I listed them here, And remember, we don't have methane. I think I wrote CH in the last class. Can anyone tell me why don't we have methane? Or like CH?
Because it wouldn't have a hydrogen. Once, if you turn it into an alkene, it wouldn't have a hydrogen.
Yes, so when we turn it to alkyne, yes, we won't be having hydrogen. But even here, if we, we want to have, like in alkenes, we have double bonds, okay? And if I want to have a double bond here, what happens here? What is wrong here?
Too many electrons for hydrogens.
What's that?
Too many electrons.
Exactly. So hydrogen can have maximum 2 electrons. So here we have like 4 electrons for it, right? So that's why we don't have, methane. But we have like ethane, propane, butane, pentane, hexane, and I listed them. So kind of like you practice. And also, if you just give me 1 second, I also show you like alkynes. And I tend to do this. Okay. And alkynes is like CnH2n minus 2. And then ethyne, so alkyne, again, your book says, it rhymes with wine. Alkyne, ethyne, propyne, 1-butene, and all of these. And then we talk about naming them and also how they can be arranged structurally in the next session. Back to the